We're starting Unit 4, which covers related rates, and the second part of the unit will be more about curve sketching. So we're relating function to its derivative and its second derivative and their curves, how they relate to each other. In 4.1, you did a review of implicit differentiation, which was from 2.7. And today we're doing 4.2, related rates, day 1. We have 3 days of related rates plus a review day of related rates as well before moving on. So this is a big topic, and we really want to make sure that we understand what we're doing here in this unit. So related rates are simply two or more variables that are related to each other with respect to time. So all of our derivatives here instead of d dx, everything is d dt, derivatives with respect to time. All right, so first example we're going to look at is not really going to be a word problem. It's just going to be a simple equation, take the derivative with respect to time, variables are related to each other. So we're going to have x and y differentiable functions of t and are related by y equals x squared plus 3. This is how x and y are related to each other. Problem is asking us to find dy dt when x equals 1 and dx dt is equal to 2. So here's something you're going to learn in these problems. The keyword when. When is a very important word in these problems. Usually you'll see the word when. Sometimes you'll see other words that represent the word when. I will point them out when we get to them. So when is going to be your keyword here. And what it means is you're not allowed to plug the numbers in that follow when until you've taken the derivative. Right, there we go. You can't plug in these numbers until after you've taken the derivative. All right, so we are going to start with the related function, y equals x squared plus 3. I'm going to bring it down here. And we are going to take the derivative of each side with respect to time. That's what a related rate is, with respect to time. So we take the derivative of the left with respect to time and the derivative of the right side with respect to time. So on the left, it's simply dy dt, okay? Or chain rule, derivative of y, 1, and then we get followed by dy dt. So we're just going to go ahead and stick with dy dt here. On the right side, we do take the derivative of x squared. We get that 2x, but chain rule follows, times the derivative of x with respect to time. So this gives us 2x times dx dt plus the derivative of 3, which would be 0. So here we go. Find dy dt when x is 1 and dx dt is 2. So now that I've taken the derivative, I can plug in these other numbers. So dy dt is 2 times 1 times dx dt, which is 2. And 2 times 1 times 2 is 4. And that's it. That's our answer. So that's how we do a related rate problem. We start with the given formula. We take our derivative first. Then we plug in any values the when statement gave us. And that's what I just did here. Okay. When we get to some application problems, those rules are the same, but we get into a few more rules that we need to follow. Okay, so I'm going to start by writing out example 2. All right, a pebble dropped into a calm pond, so at first the water is not moving, and causes ripples that form concentric circles. So the pebble hits the water, we get a bigger circle, a bigger circle, a bigger circle, and so on. Right? So you can imagine this happening in the water. Okay, we're given a rate of change here. So this is going to be important. Look for that word, rate. So these related rates are rates of change with respect to time. So anytime you see the word rate here, that's given 1 foot per second. It's a derivative. It's a dy dt, dx dt, or whatever this is. So this is the radius that's increasing at a foot per second. So the radius is changing with respect to time. So that's going to be one of our values that we're going to write out. The radius increases is important as opposed to decreasing. That'll change our numbers a little bit at a rate of 1 foot per second. So the radius changes with respect to time at 1 foot per second. So I'm going to write dr dt. So the rate at which the radius changes, so r for radius, with respect to time is 1 foot per second. So you'll see my units here. Radius is measured in feet, time is measured in seconds. Feet per second, radius over time. And that's just one of our values. All right, so let's move on to the next part of the problem. So at what rate, again, I'm looking at a rate here. Okay, so another change with respect to time. Right, so what's the rate of the area of the disturbed water? So specifically this water here. And here's our keyword when. Again, when. All right, so kind of a long problem to write out here. So when, you have to be careful here with our keyword, and only plug in 4 for the radius after we've taken the derivative. Now, you should also note that even though this dr dt came before the word when, it is a rate of change with respect to time. We're not going to get that also until we've taken the derivative. So this is not going to get plugged in until after the derivative as well. Okay. Now, they didn't tell us any formula that relates the things together, so that's something we need to know. So I need to relate the radius and my area. So we had two things here. We had the radius changing with respect to time, but we also have the area of the water changing with respect to time. So this would be the rate at which the area of the water changes with respect to time. This is what we're looking for. At what rate does the area change? Change of area over change in time. This is what we're being asked to solve for here. So I need to relate the area of a circle to its radius. And we already know a formula for that. So that formula for a circle, pi r squared. Okay, notice nothing's plugged in. The only value known is pi because it's a constant. The radius is not always the same. It depends on how big the circle is. And depending on the radius, that will tell us the area. So these two things are always changing with respect to time here. So now we'll take our derivative of each side with respect to time. Staying over here on the right as the left. So the derivative of the area with respect to time, that's just dA dt. On the right side, the only variable we have is r. So we'll go ahead and do our derivative there with r. So we bring 2 down, 2 pi r to the first. Okay, 2 pi r to the first. Chain rule applies. Times the derivative of r with respect to time. dr. So those are always going to follow. Anytime you take the derivative of any variable, you always follow up with dA dt or dr dt, or up here it was dy dt, dx dt. It's everything. Every variable. It's going to follow up with that chain rule and have those rates of change. All right. So again, we're solving for dA dt here. We want to know what this is. We have 2 pi constants. Okay, now what's the radius? Now that I've taken my derivative here, so derivative means I can now plug in my when values. So when r is 4, and what's dr dt? So that was given to us earlier. Dr dt is 1 foot per second. Okay, and I just multiply these things together. So my answer here is 8 pi, but I do need to have units. So this is a rate of change of area over time. So something per second, because I had feet per second for radius, but this is area. So it can't be feet per second again. Area is square feet. Square feet per second. So this is the rate at which the area of the water is changing at the moment when the radius is 4. So if I were to find at the moment when the radius is 5, we would have plugged in 5 here, and we'd get 10 pi square feet per second. And so it just changes depending on at what moment we're looking at. So which ring are we looking at here of the water? All right. So in this example 3, we're going to look at a classic ladder problem. So we'll start with a ladder that is 15 feet long. And it's leaning against a vertical wall. So this is going to mean we have a wall that is perpendicular to the ground here. All right. Our ladder is 15 feet long. Now, anytime you're given something like this, a 15-foot ladder, this ladder is 15 feet. This is constant. The length of the ladder will not change with time. All right, which means we get to label anything that is constant with its value. So usually we don't plug in numbers until after we've done derivatives, but the ladder's length is not going to change. This is a constant value. We get to use it. So we get to plug it in before doing anything else. Okay? All right, the next sentence says the base of the ladder is pushed toward the wall at 3 feet per second. All right, so this distance, because I'm going to be pushing the ladder along the wall, so the bottom slides in toward, the top will slide up along the wall. So these two distances here, from the base of the ladder to our wall and the top of the ladder along the wall, okay, these two distances are going to be different values as time changes. So we can't label them as constants. We're going to give them variable names. So I'll go ahead and call this the base and label it B. And this will be the height, and we'll label it H. So these things change with time. We give them variable names. Now we're told that the base of the ladder is pushed toward the wall. So I want you to understand that as the base of the ladder moves in, B gets smaller and smaller for this problem. B is getting smaller and smaller, which means the rate, 3 feet per second, has to be negative. So a rate of change that's negative here. So we're going to start with our rate of 3 feet per second, and this is for our base, so dB dt isn't positive 3, but it's negative 3. Okay, so the base is measured in length of feet. Time is measured here in seconds. So dB dt, feet per second, negative, since B is getting smaller with time. So if B gets smaller with time, I hope you'll agree that H will get bigger with time. Since this distance, the top of the ladder will get higher and higher up the wall, H would be, or dH dt would be a positive rate of change. All right, and we'll get there. So let's write down a little bit more of our problem here. At the instant when, so here's our keyword when again. We're going to watch out for what follows this word. All right, so this is going to be a several-part problem. We're going to start with, our when information. What follows can't be plugged in until after taking the derivative. So it says when the base of the ladder is 12 feet from the wall. So when B equals 12. So this is something that we can't plug in before taking the derivative. Okay. Now, the function that we need to use that relates whatever here together is going to depend on what they want us to find. So in part A, we're going to find the rate at which top of the ladder moves up the wall. So we have a rate of change here. This can't be used until we've taken a derivative. We're being asked to find a rate of change, the rate at which top of the ladder moves up the wall. So my side here is labeled as H. So the top of the ladder moving up the wall will be given by dH dt. And that's what we're being asked to find. And that should be a positive value since H is getting bigger with time. So find dH dt, what it's asking us here. Knowing dV dt and B is 12 and the ladder is 15. So what formula relates our three sides together for a right triangle? That should be the Pythagorean theorem. So H squared plus B squared is equal to 15 squared. All right, so we're going to take our derivative here of each side with respect to time. On the left side here, we have derivative of h squared, so we'll get that 2h, and every variable is followed by dh dt or dv dt. So 2h times dh dt plus, over here, 2b times dv dt. And on the right side, the derivative of 15 squared, well, it doesn't matter what that is, it's just a number. The derivative of any constant is 0. So now that we've taken our derivative, let's plug in some values here. So do we know what h is? Well, they didn't tell us. We were told when the base is 12. So if this were a nice triangle, b is 12, the ladder is 15, we can find h at this moment. So it's a little bit more information that we now have to find. So when b is 12 and when h is what? So 15 squared minus 12 squared is equal to what squared? So this value is going to come out to 9. And that's a nice Pythagorean triple there. So 9, 12, 15. So this isn't always the dimensions. These aren't always the dimensions of our triangle here, 9, 12, and 15. The ladder is always 15 feet long, but h and b are not always the same since the ladder is moving. All right. So now we're going to go ahead and plug these in. So we have 2 times 9 times dh dt, which is what we're trying to find, so that's our unknown, plus 2 times b, we're told b is 12, and dv dt was negative 3 equals 0. So there we go. We can only have one unknown. So if you were stuck thinking, well, I wasn't told h or dh dt, just remember dh dt is what you're solving for. So this really can be the only unknown. Somehow we have to know h. So you're going to go back and use information in the given part of the problem. Right? So that's dh dt minus 72 is equal to 0. So dh dt, we'll add 72 and divide by 18. Is going to come out to 4. And then that's a height over time. And heights, or our width or base, everything here in length is measured in feet. Over time, measured in seconds. So 4 feet per second. Remember, this value is positive, and it should be because my rate of change for h is getting bigger as time goes on. So that height is getting longer. So my rate of change should be positive. If my rate of change is getting smaller, then I have a negative value. All right. So that's part A of the problem. So let's continue on with part B, which is going to ask us to find the rate at which the area of the triangle is changing. All right, so a different rate this time. This one's talking about the area of the triangle. I'm going to go back up here. And now we're going to talk about this area here. So we did area with the circle. Now we're looking at the rate of the area of a triangle. So this would be a rate of change of area with time, with respect to time. That's what we want to find this time. So our formula we're going to start with is not the Pythagorean theorem. Okay, that was to find dh dt, which was a length of a side. B was the length of a side, the ladder's length also. And so our formula there was the Pythagorean theorem. Here, we want the area of a triangle. So area of a triangle, 1/2 base times height. Okay, so a trickier formula to work with, 3 variables here rather than just 2 with respect to time. We have 3 variables with respect to time. So derivative of each side with respect to time. So on the left, it is just dA dt. On the right, I'm going to keep the 1/2 constant. I can keep it outside or I can lump it in with the B. I'm just going to put it outside here, 1/2. And then take the derivative of B times H. So for that, we need the product rule. Okay, so product rule for B being our first term and H being the second. So 1 and 2, we have the first times the derivative of the second, dH dt, plus the second H times the derivative of the first, dB dt. All right, so here, if we're solving for dA dt, we should know the rest of these values. So now that I've taken my derivative, I'm in my when stage. I can use the given information here from the when sentence. So B will be 12, H will be 9, dB dt is -3, and then dH dt we just found in part A was 4. So we're just going to plug in all 4 of those values here and simplify. So we have that 1/2 out front, and we have the values we're looking for here. So B was 12, dH dt we just found was 4, plus H, which was 9, part of the when statement that we had to figure out. dB dt was given information in the state problem, -3. Okay, and we just want to simplify all of this here. So dA dt is going to come out to 1/2 of 48 minus 27, which isn't perfect, but that's okay. We have here 21/2 or 10.5. And then we just need our units. So we're talking about the area changing with respect to time. So something over time, so something per second. Now our lengths were all measured in feet, so our area is measured in square feet. So 10.5 square feet per second is the rate at which the area is changing. Okay, and then we'll do one more part here, part C of this problem. So So this one is going to ask us to find the rate at which angle formed between the ladder and wall is changing. Okay, so a new rate of change that we're looking at here. So rate of an angle between the ladder and the wall. So if I go back up to my drawing, okay, this angle is up here at the top. So this is the ladder, this is the wall, this would be the ground. So this is theta here, so our angles. So we need to give it a name. I'm going to call it theta. You could call it whatever variable you want to call it. So if I want to find the rate at which my angle changes with respect to time, I'm going to be looking for d theta dt. I'm looking for d theta dt. So this time, I need a formula that relates theta to some of the values I have. So I can either use h, b, or 15, and it just depends on what function you want to work with. Because to get the derivative of theta, an angle, we'll have to take the derivative of whatever formula we come up with. So how do I relate an angle to my sides? By using trig. So we can do sine b over 15. We can do cosine h over 15. I could even use tangent, which would be b over h. And I wouldn't use tangent because then you're using two unknown variables besides theta. So you'd have, again, three variables that you'd be working with. So use sine or use cosine. Just depends on which one you want to take the derivative of. So let's do sine. Sine will be easy. Sine theta equals b over 15. So we're going to start there. So that'll be our equation that relates them together. So opposite over hypotenuse. Remember, we get to use that 15 because the ladder is always 15 feet long. It's not changing. So let's take our derivative here of each side with respect to time. All right, derivative of sine will be cosine. And then chain rule applies. We got to go inside of sine is theta. So derivative of theta with respect to time will give us d theta dt. So we have now cosine theta times d theta dt. Now on the right side, I don't need to use my quotient rule because it's not a ratio of two variables. Rather, it's 1/15 of b. So it's just a number in front of my variable. So when I do my derivative, okay, so let's think about it this way. 1/15 of b that I'm taking the derivative of. So the 1/15 is just the coefficient, so the coefficient stays. Right? We get 1/15. Your power 1 would come down, drop b by a power to 0. B to the 0 becomes a 1. But then again, our chain rule follows, and dB dt follows this up. Right? So again, if I were just doing the derivative here, we'd just get the coefficient, but chain rule follows, dB dt is in the problem. So now we're responsible for solving for d theta dt, which means I have to know the rest of the values in this problem. So I have to know what cosine theta is, and I need dB dt. So dB dt was a given part of the problem, -3. Now we just need to figure out what's cosine theta at this moment. So at this moment, we have B is 12, H is 9, and the hypotenuse is 15. So let's write that over here. B is 12, H is 9. So cosine of theta is adjacent over hypotenuse. So that would be 9 over 15. So again, I couldn't have used this information before I started the problem because I had not taken the derivative yet. Now that we have, cosine is 9 over 15 times d theta dt is equal to 1/15 times the given dB dt, which was -3. And we're just going to solve by simplifying this, so I'll multiply across by 15 over 9. Okay, and this will simplify to -1/3. And it's a rate of change over time, so something per second again. Now, on top, it's theta. Theta is an angle, and angles are measured in radians, not feet. So this is radians per second, so a bit of a different unit here, -1/3 radians per second. So if you think about that, why is it negative? Why is my rate of change negative? It must be because theta is getting smaller with time. So as our ladder's base was being pushed in, the height is being pulled up, and that angle, as the ladder moves in, is getting smaller with time. And so I'm getting a negative value here. Okay, so that is a ladder problem. There's 3 different types of questions you can be asked, and depending on what kind of question you're being asked, the formula you start with will be different.